Swayam Prabha. Digital India. Educated India.
So, let me continue with whatever we were doing last time. See, I was explaining to you the Gauss-Bonnet theorem, okay, a very general version of Gauss-Bonnet theorem. So, we have already seen Gauss-Bonnet theorem for surfaces, which says that essentially the total curvature is given by it depends on the Euler characteristic, okay, and I was trying to indicate last time how that Gauss-Bonnet theorem for surfaces can be gotten by triangulating the surface into small curvilinear triangles on the surface, okay. And so you need a Gauss-Bonnet theorem for curvilinear triangles, and I was explaining that, and I told you that it is a generalization of this very simple thing that the sum of three angles of a triangle is 180 degrees that you see in ordinary plane geometry. So there is, so I told you, for example, that if you are going to take a triangle whose edges are geodesics, okay, then the curvature involved is only the Gaussian curvature of the surface of the triangle, the interior of the triangle. But when the edges are not they are not geodesics, then what happens is that you have to also add the contribution due to the geodesic curvature of the edge curves, okay. And from this you can see something, you can infer something. So it's just a remark, I did not mention it last time, but let me mention it. You can guess that if the curves are geodesics, then the geodesic curvature will be 0. Okay, there is no contribution due to the geodesic curvature. So in other words, geodesics are not only the curves of shortest path, shortest distance, they are the shortest distance, but they also have this property that for a geodesic, the curvature is completely only in the normal direction. I told you curvature has of a curve on a surface will be pointing in some region, some direction in space, and it has two components. There is a normal curvature which is a component along the normal to the surface, and then there is something tangential to the surface which is called the geodesic curvature. Okay, and for a geodesic, what happens is that the geodesic curvature is 0. That is only normal curvature. And why the geodesic curvature is 0 is because you see it's a geodesic, so it's shortest distance, so it does not waver on the surface. That's why you are getting the the shortest distance. Okay, you must understand that. So geodesics are not only curves of shortest distance, they are also the curves for which the full curvature is just the normal curvature and the geodesic curvature is 0. Okay, that's why the contribution due to geodesic curvature of the edge curves, okay, that appears in the Gauss-Bonnet for, let us say, polygonal curves, or curvilinear triangles or curvilinear polygons on a surface. There is a term which corresponds to the geodesic curvature of the edge curves. That term disappears when the edge curves are geodesics. Okay, so this is a fact that I think if you think about it, it's obvious, but it is also true. So I just wanted to say that, but we will come to characterizing geodesics later. Okay, now what I want to do is, as I told you last time, I want to now start from this lecture formally start doing the theory. Okay, and first we will study curves. Okay, and then we will study surfaces. And when you study curves, let us first worry about plane curves. Okay, and then go to space curves. Okay, so our first task is trying to understand what curvature of a plane curve is. Okay, so let me write that down. So curvature, so curves, curvature of a curve. So you have to understand what is the curvature of a curve. All right, now you see now we have to make everything mathematical. Okay, so you have to now make definitions. So the first the question is that what are we thinking of? So we are on the plane, and I'm drawing a picture here, and then this is the xy plane, and we are looking at some curve. All right, and there is some point on the curve P naught, let us say, all right, and at that point you are trying to find the curvature, and you know the way to do it is geometrically find the best fitting circle which is tangent to the curve at the point P naught. That means find a circle whose tangent at P naught, a circle passing through P naught whose tangent at P naught is the same as a tangent to the curve at P naught, and the circle, of course you can find many circles, but you have to find one that is closest to the curve, that is the best fitting circle. That should be the circle of curvature, and its radius will be the radius of curvature, its center will be the center of curvature, and the reciprocal of the radius of curvature will be the curvature. Okay, so that's the strategy. Okay, so I have a picture like this. So at this point I have a I have a circle here, and then the circle has a center. Okay, the center of curvature at P naught, and then of course this so I'll draw it like this. I don't have much space, but it's okay. So this is the circle of curvature, and then this is the center of curvature, and of course both the circle of curvature and the given curve pass through P naught, and they have common tangent at P naught, and of course you also have that if I join this, this is the radius of curvature. This is r of P naught, okay, and this is equal to 1 by the curvature at P naught. So we agreed that the curvature is to be defined as reciprocal of the radius of curvature. Okay, so this is the picture that we are having in mind. The point is, what are the unknown quantities? You have to find the center of curvature, you have to find the radius of curvature, reciprocal of which will give you the curvature, and you have to find formulas for that. Okay, so the first thing is that you have to represent this curve mathematically. So how do you represent a curve mathematically? A curve is just a one-dimensional object. So the easiest way that you represent a curve is the so-called parametric representation. So you represent the curve as a parametric representation in terms of one parameter, because it's a one-dimensional, essentially a one-dimensional object. So basically how this curve is defined is that you take an open interval a comma b on the real line, and then you take a function gamma which is continuous. Okay, you take a continuous function gamma. Okay, so it is, the curve is just this is a continuous curve, it is just the continuous image of an interval. Okay, and mind you, what does this do? You give me any t here, gamma will send it to gamma of t. So gamma of t will be a gamma of t will be a moving point. Okay, and as t goes from a to b, okay, gamma t, the point gamma t will trace the curve in a certain direction, and that is the orientation given by increasing t. All right, and t is the parameter. All right, and you are familiar with these kind of parameterizations, and I should tell you, gamma t is now, you see, you can think of it is a point in the plane, so it has two coordinates. So this gamma t will have two coordinates, which are the x coordinate and the y coordinate, and they will depend on t. So you can write as xt yt. All right, and saying gamma is continuous is the same as saying both x and y are continuous functions of t. Okay, so that is the definition. Gamma continuous if and only if x and y are. So let me put the argument. Let me write it as gamma of t continuous in t if and only if x of t and y of t are continuous in t. Okay, so that is what it means. All right, so as t varies continuously, both xt and yt vary continuously. Okay, so this is the this is what is called a parameterization. So of the curve. All right, and t is the parameter, and of course you are worrying about the curvature at a point p naught, which corresponds to t equal to t naught. So this p naught is just gamma of t naught. Okay, so this is the situation. Now the point is, I want to get this circle of curvature. All right, so how do you do it? So how do you do it geometrically? See, you can see that mind you, we have to show that such a circle exists. Okay, and it is unique, and you have to get the and if it really exists, you have to find the center of the circle of curvature and the radius of curvature. Okay, we have to do that, we have to establish this. Okay, now of course the motivation is that what you are trying to do is at the point P naught, you are thinking that the part of this as a particle or an object moving, a point object moving along the curve. At that point P naught, there is an instantaneous velocity and it is turning. Okay, so the idea is that you want to instantaneously, approximate it to a circular motion at that point, and you want the circle basically. Okay, so if you think about it, what are the so let me draw another picture here, which a slightly bigger picture. So you see, here is my curve, and here is my point P naught, which is gamma of T naught. Okay, at the point gamma of T naught, you have a tangent vector. Okay, so as you are moving along the curve, okay, at every point you have tangent vector. So for that matter, if you take a point as gamma t, which is x of t comma y of t, okay, then how do you get the tangent vector at the point t? This tangent vector is going to be just by you just have to differentiate with respect to t. Okay, so the tangent vector is going to be just given by the vector x dot of t, y dot of t. Okay, so what is this x dot of t? The notation is dx of t by dt, and y dot of t is dy of t by dt. And of course, why does this give the tangent vector? This is just by definition of the derivative, because if you take the point gamma of t here, okay, and you take a nearby point gamma of t plus delta t, okay, and then if you join this, you look at this this direction, this vector, okay, then this is going to be given by gamma of t plus delta t minus gamma of t, okay, as if you think of gamma t and gamma t plus delta t as position vectors of those points. So there is a dual point of view, a parallel point of view that we will always take. We will think of whenever it is convenient, we will think of a point on the plane also as position vector of that point. Okay, so this gamma, when I write gamma t here, this gamma t is also a pair of coordinates. It's also the position vector of the point given by gamma t. So in other words, you can also write gamma t as x of t I cap plus y of t j cap, where I cap and j cap are the unit vectors along the x and y axis. Okay, so you have to be flexible to think of it as a vector and also as a point. All right. So if you think of it like this, then gamma of t plus delta t minus gamma of t is this vector from p of t to p of t plus delta t. Okay, and what is this? This is going to be, if you write it in coordinates, it's going to be x of t plus delta t minus xt, that is the x coordinate, and that is the x component, and y of t plus delta t minus y of t, this is the y component. All right, and how do you get the tangent? You have to basically this chord becomes the tangent as delta t goes to 0. Okay, and of course so see, this is the if you simply let delta t to go to 0, then gamma of t plus delta t minus gamma t will also go to 0. Okay, the point is I want that direction. Okay, so basically what I have to do is I have to keep these when you take a vector and take its components, the components give the directions basically of the vector. So what you need is, you need the limiting values of these two, okay, as delta t goes to 0, all right, or rather you need the ratio, okay, and the way to get the ratio is, see, you divide by delta t, okay, dividing by the same number, a ratio, two quantities will not change its ratio. So what you do is, don't directly let delta t go to 0, it will not help you, okay, but geometrically it does. As you let delta t go to 0, this chord p delta t d becomes if you don't take the chord, you take the whole line, that becomes the tangent at p, right? But I have to keep track of those ratios. So what you do is that this ratio, the direction is still given by x of t plus delta t minus x of t by delta t, and y of t plus delta t minus y of t by delta t. And when I write this is when I write equal, I mean same direction. Okay, and you understand why I am doing this, because Now if I let delta t tend to 0, then this is not going, this is going to give me something. And what are they? They are the ratios, two-dimensional direction ratios of the tangent vector, all right, which is, if you think of t as time, then it's you are just writing out d gamma t by dt, and if you think gamma t as displacement, d gamma t by dt is nothing but the velocity. So it is the tangent vector is just physically the velocity. If you think t as time and gamma t as position, then this is d gamma t by dt, and that is what I want to call as gamma dot. So this is exactly going to give you x dot of t, y dot of t. Okay. So I am just trying to tell you something that you already know, that the tangent vector is just given by gamma dot of t, which is x dot of t, y dot of t. All right. So I just want to say that, suppose the origin is somewhere here, okay, then you think of gamma t as this vector, okay, and then you think of gamma t plus delta t as this vector, okay. Then by the triangle law, this vector, okay, this vector is gamma of t plus delta t minus gamma t. And since gamma is continuous, if you just let delta t to go to 0, you are going to just simply, since gamma is continuous, limit delta t tends to 0, gamma of t plus delta t will be equal to gamma of t. So if you just let delta t go to 0, this will become 0. But that's not what you want. What you want is, you want this idea that this chord, okay, this whole chord, the chordal line, that limits to the tangent at that point, and you want to keep track of the slope of that. And to keep track of the slope of a vector, you have to keep track of its components. Okay, of course, in 2 dimensions, the slope is given by the y component divided by the x component. Okay, so but instead of taking it like that, you can the idea you very well know the idea of direction cosines for a direction in 3 dimensions. Okay, basically you are taking cosines of the angles made by that direction with the 3 axes. The same thing works also in 2 dimensions. Even in 2 dimensions, you have direction cosines, and these are nothing but the the coordinates. Okay, so the coordinates, if you keep track of the coordinates, they give the direction. So what I want is, I want to keep track of these coordinates, but I want to keep track of it in as delta t goes to 0, and I don't want it to become 0. Okay, so the trick is that you because these are ratios, you divide both by delta t. Okay, so you see this thing has the same direction as this. After dividing by delta t also, you see the direction doesn't change, because you have just made a scaling of both x and y. All right. So then if you take delta t goes to 0, advantageously now you are not going to get 0 0. Okay, you are going to get the x dot and y dot. Okay. So you see, therefore this is just this is how see, already here calculus has come in to rescue you. Okay, that this trick of dividing by delta t and letting delta t tends to 0 allows you to keep track of the tangent, keep track of the direction of the chord and then limit it to the direction of the tangent. Okay, so you have to appreciate that. So you see, so this as delta t goes to 0, this implies that the chord becomes the tangent. So I am using TGT for tangent. Okay, so that's the idea. All right. So, and if you think of t as time, okay, then gamma and gamma t as position, displacement vector with respect to a fixed position vector. In this case, with respect to the origin, if you want, and you take the usual position vector, displacement vector, then this is nothing but rate of change of displacement vector with respect to time. So this is the velocity. This is the velocity of gamma at t. All right. So this is your tangent vector. Now you see, so you see what we are going to do. See, at the point p naught, I have this tangent vector at t naught, at p naught, which is gamma dot of t naught. That will be the tangent vector. All right. And of course, when I say tangent vector, I am taking x dot of t naught, y naught of t naught at t equal to t naught. All right. At the moment, I am not really worried about the length of the tangent vector. Okay, but I am just taking the direction. All right. Now, see that what is the starting? What is the clue? The clue is that this circle of curvature see, it is a best fitting circle at the point P naught, and that circle is also having the same tangent at P naught as the curve. Okay, that means that for that circle, you see, if I take the center, which is center of curvature, and join it to P naught, that will be normal to the circle, of course, and it will also be normal to the curve, because at that point both the curve and the circle have the same tangent, they have the same normal. So there is one clue as to where to look for the center of curvature. The center of curvature has to lie on the normal to the curve at that point. Okay, you can see that. So therefore what I can do is, I can draw a normal like this. Okay, this is the normal, this is the normal at T naught. Okay, and the center of curvature is somewhere, it's supposed to lie somewhere here. All right, now the point is, I have to find that center of curvature. See, once I find that center of curvature, I have to show it exists. Okay, I have to find that center of curvature. Once I find that center of curvature, then my job is done, because then I know this is the center of the circle. I know it passes through P naught. I just draw the circle, and everything is done. So the aim is to get that center of curvature. Okay, so how do you do that? So the geometrical way of doing it is the following. Basically, what you do is that there are let me tell you the general geometric idea. The general geometric idea is, you see, you have a curve like this. Okay, and there is this point P naught. All right, how will you find the circle of curvature at that point? All right, what you do is you can take three points. Okay, let me call this as P1, P2 and P3. I can take 3 points which are close to P naught. Okay, and assuming that the curve is really curved around P naught, I can take them sufficiently close so that those 3 points are not collinear. Okay, and since those 3 points are not collinear, they pass through a circle. So what happens is that through P, so it's somewhat hard to draw, but so I will draw something like this. So let me do the following thing. So basically, it's like, I have a triangle like this, and there are these points P1, P2 and P3. Okay, and these are nearby points on the curve. Okay, so let me first draw the. So for 3 non-collinear points, there's always a circle passing through that. Okay, so what I can do is, that is the the circumcircle of the triangle. So I can draw this circumcircle. So let me draw it as best as I can. Okay, so this is circumcircle of the triangle. All right, and you see the curve itself, is passing through these 3 points. So your picture is like this. So here is the curve. Let us say, somewhat hard to draw, but let me try drawing it. So something like this. Oops, yeah, it's hard to draw these things, but I'll nevertheless try. So here is your curve gamma of t. All right, and the curve passes through these 3 points P1, P2 and P3. Okay, and they are all the 3 points are, let us say, close to the point P naught on the curve which I am interested in. And let me be careful. This P naught may the circle may not pass through P naught. Okay, so now what you should expect is, as this P1, P2 and P3 slowly approach the point P naught, you should get a limiting circle, and that limiting circle is going to be the circle of curvature. Each center is going to be the center of curvature. So geometrically, you expect this to happen. Okay, and if you think about it, this is the most general geometric way of getting the circle of curvature. At a point on the curve, you take 3 nearby points, and if the curve is really curved, you will get 3 non-collinear points. There is a circumcircle for that. And now vary these 3 points independently so that they all come and coalesce, they all limit to that point that you are interested in. Then this circle will limit to a circle, and that circle will be tangent to the curve at that point, and it will be the circle of curvature. Okay. Now, of course, this is something that needs to be proved either by using some geometrical properties of circles and triangles or something like that, or we will have to use calculus, but this works. Okay. Now, what I want to do is I want to attempt giving you a proof that is completely bare hands, a very simple proof, and for that I am going to do the following thing. See, first of all, in this, so let me write this. So this I write this as C. I'll write this as C of P1, P2, P3. This is a circle. So let me put. So I'll just write. Let me use C. Let me write circle P1, P2, P3, and the C of P1, P2, P3 is actually the the center of the circumcircle. So C of this is the circumcircle, okay, and this is the center of that, and the claim is as P1, P2, and P3 approach P0, then this this circle P1, P2, P3 gives you in the limit the circle of curvature, and this its center gives the center of curvature. So as so I will write here P1, P2, P3 close to P0 as P1, P2, P3 tend to P0. Okay, circle of P1, P2, P3. So if you want, it is circumcircle. Circumcircle P1, P2, P3 goes to circle of curvature at the point P0, and the center of P1, P2, P3 goes to center of curvature at P0. Okay. So this is the geometrical approach. All right. And of course, in this geometrical approach, you see that it's not entirely geometrical. You are saying in the limit something happens. Okay. And trying to make sense of this, that it is happening in the limit, there are geometrical arguments, but the easiest arguments involving limits use calculus, and so we are going to use one such argument. Okay. So here, so notice one more thing. See, if you it's more or less obvious that for the 3 points other than the point P0, you could have taken one of the point to be just P0 itself. Okay, and then if you look at it, okay, you so something interesting is happening. Okay, if you just look at just P0 and two nearby points P prime and P double prime. Okay, then, and the center of curvature has to lie on the normal at P0. Okay, so so basically what happens is there is a normal. So this is a normal at P0. Okay, then there is a normal at P1. So yeah, so and so I have to draw 3 of them. So let me draw them, and yeah, so I'll have to. So this is normal at P1. Let me say like this. Oops. So you see there is, so let me make it look more clearer. So let me get rid of this. So this is so P0, so it's P dash and P double dash, or you could have taken it as P1 and P2 anyway. So let me keep it as P dash and P double dash. Okay, so here is the so this is, so let me label this. This is the normal at P0. Okay, this is the normal at P double dash, and this guy is the normal at P dash. Okay, see, you are getting these 3 normals, and the point is that you should always remember that the center of curvature is supposed to be on the normal at P0. Okay, so basically, it's these 2 points that that will change as I change P dash and P double dash. If I make this P dash and P double dash come closer and closer to P0, okay, then these 2 points will change. Okay, and in fact, there is also this 3rd point here. So there is this nice little triangle. And what you should expect is that this triangle, you see, should degenerate to a point, and that point must be the center of curvature. That's what you expect. And in particular, if you believe it, even if I considered only the normal at that point and a nearby normal, okay, then that point also should in the limit go to the, when a triangle is degenerating to a point, then all the three vertices are degenerating to that point. Okay, so in principle you should see that this should be doable having just one point and the normal at one other point other than the point P naught. Okay, so all I could have done is just taken a nearby point and drawn the normal and taken the point of intersection with the normal at P naught, and then try to examine what happens as the nearby point approaches P naught. Okay, so that is the viewpoint that we are going to take as inspiration from this. Okay, so what I am going to do is I am going to take a nearby point. So let me write this nearby point as P, which is gamma of t, which is I will write this as so this is at nearby point. So at P naught the parameter value is T naught, small change the parameter is delta t, so I will write this as gamma of T naught plus delta t. Okay, and what happens is that at this point you are going to get a normal. So I'll draw this normal here. Somehow I'm going to get a normal. It's not really, doesn't really look like a normal, but let me draw it like this because I want it to intersect, and I'm worried about this point here, this point of intersection. Okay, and so you see this is so again I need to so let me draw this as normal at T naught plus delta t. This is the normal at T naught plus delta t at the nearby point P, and this is of course the normal at P naught, which is this. Okay, and this is the point of intersection. Okay, now what you should guess is that, of course, it's quite funny if you think about it in one way. As delta t goes to 0, you see the normal at T naught plus delta t will tend to the normal at P naught, which is a normal at t equal to T naught. Okay, and then you can expect that this point of intersection may go to infinity. Okay, you can expect that as these things come together, this intersection point goes to infinity, but it doesn't. It goes to a finite value. Okay, that's the magical thing. Okay, it goes to a finite point. It has a limit. It has a nice limit, and that point is the center of curvature. You get it. Okay, now this is something that you have to establish using geometry and calculus with some assumptions on differentiability, which is what I'm going to attempt to do. Okay, and that is going to give you a first formula for the curvature of a curve. All right. So again, I want you to notice at every point, you see, there is no guarantee that as this point, there is P naught, there is a normal at P naught, then there is the nearby point, and there is a normal there. There is no guarantee that the point of intersection will just stay to a finite limit. Okay, it might just go off to infinity, because after all these two lines are becoming one and the same. They are becoming parallel, so you can expect that this point to go away to infinity. It doesn't. Okay, so that's already something that is somewhat mathematically does be proved. Okay, so it's that way it's kind of interesting. It doesn't fizzle out. So we have to prove this. Now how do you prove this? It's now it's a game of plane geometry and some calculus. So basically what you do is that you write the straight line equations of these two normals, okay, and try to solve for the point of intersection. Okay, and then you have to play with calculus carefully. Okay, so let's do that. So let us call this point of intersection, okay, the point of intersection of the normal at T naught plus delta t and the normal at T naught. Let us call this point of intersection as x of delta t and y of delta t. Okay, so please be so x of t, y of t are already the coordinates of gamma of t. So if this is somewhat confusing, let me put a tilde there. Okay, so that so x tilde of delta t and y tilde of delta t is the point of intersection. And what the claim is, you let delta t go to 0, then this x tilde delta t, y tilde delta t goes to at t equal to t naught. Mind you, as delta t goes to 0, you are approaching the point t equal to t naught. Okay, t naught plus delta t goes to t naught, and you are supposed to get a particular point. So with coordinates x tilde t naught, y tilde t naught, which is the center of curvature. Okay, so here is a claim. So the claim is so let me write this. So let me write it. This claim is, as you know, this p goes to p naught, that is delta t goes to 0. Okay, this point x tilde delta t, y tilde delta t goes to some point, some specific limit x tilde of t naught, y tilde of t naught, and this is going to be the coordinates of the center of curvature. At t equal to t naught or at p naught. Okay, so that is the claim. Okay, and again, it's interesting that as these normals become parallel, the intersection point doesn't escape to infinity. You get a finite limit. So let's write out these equations. So what are the this is a matter of plane geometry. So let's write the equations. So you have this curve here, gamma t, and I have this point p naught, which is gamma of t naught. The coordinates are x naught, x of t naught, y of t naught, which I will abbreviate to x naught comma y naught. Okay, so x naught y naught is abbreviation for x at t naught, y at t naught. All right, and always the subscript 0 means that it is a value at t equal to t naught. Okay, let's keep that convention for ease of notation. Okay, so this point is x naught comma y naught, and you know that what is the tangent direction? The tangent direction is given by x dot t naught, y dot t naught, where this dot means derivative with respect to t. Okay, so I have to say something here. So I have to get back here and say something more. Originally I started only with a continuous curve, and that means that and I told you gamma continuous in t is the same as saying both the functions xt and yt are continuous with respect to t, but now I want the tangent. So I want to make sense of x dot and y dot, which is dx by dt and dy by dt. So continuity is not enough, so I need differentiability. Okay, so you see that from this your gamma should be first differentiable. But gamma has two components, x and y. That means both the x and y, they should be first differentiable. Not only that, that first derivative gives a tangent, and I want the tangent to move smoothly. I mean, I at least I want the tangent to change continuously. Okay, see, always remember that whenever you draw a curve on paper, it is at least piecewise continuously differentiable. Because if the tangent is not continuously turning, you cannot draw it. Okay, the way you draw a curve, okay, is always in a continuous, nice, smooth fashion. The only way you can break it is like joining several smooth piecewise smooth curves at corners which you purposely introduce by changing the direction. But otherwise, how do you draw a curve? Basically, if you look at it, what I am doing is that I am giving a uniform, not uniform, let's say continuous velocity to this. Okay, and that means my basically I am giving you a continuously varying tangent direction. Only such curves you can really draw. So we will assume that we will have to assume that anything that is differentiable is also continuously differentiable in that sense. So differentiability will tell you that there is a tangent at every point, but I want the tangent at every point also to change continuously. I don't want tangent at one point to be very discontinuous when compared to the tangents at nearby points. So it means that this gamma is not only first differentiable, it's first differentiably continuous. So you have to now put the condition that gamma is C1. Okay, all right. So let me write it here. Existence of tangent to curve at gamma at t, this is equivalent to gamma dot of t existing. Okay, and what we want also the tangent directions to change continuously. So gamma dot should be continuous. Okay, so this implies that gamma should be in C1 of AB. So this is the notation. C1 of AB means all those functions, real valued functions on the open interval AB, which are not only differentiable but the derivatives are continuous. Equivalently, this is the same as saying x dot and y dot must be continuous. And why do you want tangents to be continuous? You see, you know what you are trying to get. You are trying to get this center of curvature by letting delta t go to 0. But what is that point? Is the intersection of normals. It is the intersection of the normal at that point where you want the center of curvature and a nearby point. And you see, the intersection of these two, you want it to have a limit. Normally you will have a limit only if there is continuity. Only if the nearby normal is going to continuously go to the normal at that point, okay, only then I can expect to have a limit, because limits are the same as continuity. But you see, nearby normal being going continuously to the normal at the point is the same as nearby tangent going continuously to the tangent at that point. That means the tangent has to be continuous. That is the reason why you need not only the tangent to exist, but you need the tangent to be continuous. Therefore, you need a C1 function. Okay, so you see, all these hypotheses are geometrically motivated and they get into the the theorem, the final result. So I am now going to assume that gamma dot exists and the gamma dot is also continuous. All right. Okay, so that is so we will go back and forth to put hypothesis as the geometry suggests, and finally get to this. And this is going to teach us some very important lessons, as we will see when you try to formally define the curvature of a curve. All right. So here it is. This is the tangent direction. Okay, this is the tangent at t naught. What about the normal direction? Okay, so for the normal direction, you see, I need the equation of the normal here. Okay, this is a normal at t naught. How do I get the equation of the normal? See, already I know it passes through p naught. I need only the slope. Okay, and for the slope, what I will do is that it's the slope of a perpendicular line. Okay, so the slope of the tangent line is y dot of t naught divided by x dot of t naught. Okay, this is the slope of the line. Okay, and of course, whenever I am dividing by something, it's kind of understood that the denominator does not vanish. All right. And what is the slope of the normal? Slope of the normal at t naught is going to be minus x dot at t naught by y dot at t naught. This is the slope of the normal. All right. Because perpendicular lines, product of slopes is -1. So the slope of this must multiplied by the slope of the tangent should give you -1. So this is the slope of the normal. Okay, and you see that for this to you can see more or less for this to make sense that if it is the slope of the normal that I am seriously interested in, then you see this y dot of t naught, which I have written in the denominator, that should not vanish. Okay, and if I want to make sense of the slope of t naught also, okay, x dot of t naught also should not vanish. All right, and because I am dividing by these things, and what you must understand is that since x dot and y dot are continuous functions, okay, and since by continuity, if a continuous function doesn't vanish at a point, it will not vanish in a neighborhood. That's continuity. Okay, so if a continuous function doesn't vanish at a point, it cannot vanish in a neighborhood. Therefore, x dot and y dot not being 0 at t naught will tell you that there is a small interval around t naught in the interval AB where both x dot and y dot should not vanish. Okay, so this is by continuity. Okay, so you see, I'm going to assume that x dot of t naught is not equal to 0, y dot of t naught is not equal to 0. This implies by continuity of x dot comma y dot at t naught, x dot of t is not equal to 0, and the same holds for y dot of t for all t in an interval surrounding t naught in AB. Okay. So this is, see, here is where the fact that gamma dot is C1 is being used. Okay. And of course T naught is just any point that I am worried about, so basically I need gamma dot to be continuous everywhere. So here is another point, technically, where the continuity is used. If a continuous function doesn't vanish at a point, it cannot vanish in a neighborhood. Why? Because if it vanishes at a point in every neighborhood of a point, then you have a sequence of points approaching this point where the value is 0, and by continuity, therefore at that point also the value must be 0. But therefore, if a continuous function didn't vanish at a point, then there is certainly a neighborhood surrounding the point where it cannot vanish. Okay. So this is continuity working for you, and here I need continuity of gamma dot, okay, not just of gamma. Okay, that's why you need gamma to be C1. Okay, all right. So with that backing, I now have the normal and tangent. Now once I have the normal and tangent, I can write the equation of the normal. So the equation of the normal at t naught, what is it going to be? It is the point slope form. So it is y. So what I will do is so you see, the aim is, of course, I have p naught. I have the point p naught, which I know, and I have the normal slope. I can write the equation of the normal in taking this p naught, but I don't want to do that. I want to take the equation of the normal with respect to the other point, which is the center of curvature, which is what is the variable that I have to find the value of, okay, the limiting value of. So what I will do is I will take this point, which is supposed to be the lying on the on the normal, and it is going to limit to the center of curvature. So what is this point? I wrote it as x of delta t, y of delta t. Okay, mind you, the way this point was gotten by was intersection of the normal at p naught with the normal at a nearby point. So basically there's one more. So there is also this other point here. So let me write that also. There is this gamma of t naught plus delta t. Okay, that's a nearby point p, and at that point also I have the tangent. So this is gamma dot of t naught plus delta t. Okay, that is a tangent, and there also you have the normal. And so this guy here is normal at t naught plus delta t, and this guy here is normal at t naught. So let me erase this. Okay, and the intersection, and the intersection is supposed to be what I am interested in, which is which is supposed to give me the center of curvature as delta t goes to 0. Okay, so I will, when I write the equation of this normal, I will use that point because that's the point whose coordinates I have to find in the limit. Okay, so you see what will be the equation of the normal? The slope is minus x dot t naught by y dot t naught, and it is passing through this point x of delta t comma y of delta t. What is it going to be? It's going to be y of delta t minus y naught by x of delta t minus x naught is equal to minus x dot of t naught by y dot of t naught. Okay, I get this. All right, and let me write the function, the slope function. Usually the slope is written as m, right? Y is equal to mx. So let me write this as m is equal to m of t. Okay, and this is going to be x dot of t by y dot of t, minus x dot of t by y dot of t. This is the slope of the normal. All right, and if I write it like this, this is in that sense this is just going to be m naught, which by our convention is m value at t naught. So, m naught is m of t naught, which is minus x dot of t naught by y dot of t naught. Okay. So, now, so this is the equation of the normal at t naught. Similarly, write the equation of the normal at t naught plus delta t. Okay. And if you write it, what will you get? You will get a similar equation. You will get y of delta t minus y naught plus delta y, okay, by x of delta t minus x naught plus delta x. Okay. This is equal to, you will get m naught plus delta m. So, you see this for the nearby normal the slope changes, and that change you are going to call it as delta m. So, you get this as the equation of n t naught plus delta t. Now, all you have to do is solve for x of delta t and y of delta t from these two equations. Let delta t go to 0, and lo behold, you have the center of curvature. And the point is, calculus will ensure that you will get a limit, okay, and we have to see that. So, we will see that in the next lecture. Okay. So, we will continue in the next lecture.